or something.
Okay, so I think we're streaming.
We can look at that after. Yeah.
And then let me copy the link for this. There we go. Okay, share. Gotta make sure I'm not leaking anything. Okay, so that's the stream. So now we're gonna close the screen. Close this, close this. Pop that back open. And okay. Hello everyone. Welcome to the spring 25 semester of, I need to plug this back in for everyone that's here. But then, welcome I guess everyone online to the spring 25 semester of HACC. So today's meeting is going to be about the NSA Codebreakers challenge. This is a challenge I worked on all last semester, so it's going to seem really, really complicated, but keep in mind I had like 4-ish months to try and complete everything. So I spent a lot of time working on these challenges and trying to figure out how things worked. So hopefully you guys will learn a ton. I guess notable things, internationals are going to be happening soon. I know not everyone is able to make it, but I think it would still be worthwhile coming and watching the teams compete and checking out how things work, because this is going to be a much higher level competition with a bunch of other colleges and other people. And other than that, any other announcements we really need?
The Olympiad.
Oh yeah, if anyone wants to help make some ciphers for the Science Olympiad, which is where a bunch of middle schoolers compete in a bunch of different scientific competitions, I have been asked to kind of help facilitate it by developing ciphers and then overseeing what's going on April 5th, where they're all going to be trying to compete and win. There will be about, I think, 405 people there during the competition, so it's actually pretty big. So if anyone else wants to kind of check that out and help with it, that'd be super cool. Otherwise, I think it's time to get started. So, what is Codebreakers? Essentially, it's a challenge put on by the NSA. I believe it's pretty much for recruitment, so it's meant to be hard and it's meant to show that you are worthy of the NSA's time as far as like the hiring process goes. Each challenge is based on the previous one, and they all kind of build upon each other and get progressively harder as you go along. So you'll kind of watch, if you see the amount of people who solve task 1, task 2, task 3, it's usually like 10% of people who have solved the previous task can solve the next one. So it gets a lot harder each jump. So don't feel bad if like you solve task 2 and then you get to task 3 and you're completely lost. That's kind of how it just normally is, how it's supposed to be. And as they say on their website, it is not based on real events. This is not something that the NSA had to do and then they just kind of changed a couple of names and threw it up for us to work on. This is all a fictional thing. This isn't, leaking any government secrets or anything. So here's the scenario. I'm not going to read it all out. It's kind of wordy, but if anyone wants to pause later on and kind of read this, or sign up because the challenges are still available if you want to work on some of these yourselves and kind of look at what there is to offer. I think that some of the challenges also have some really cool extra information around them, even if you already know how it's solved, especially task 2 and task 4. Both of those have some really, really cool, just kind of miscellaneous things that don't apply to the challenge at all, but will help you learn a ton. So I think they're still worthwhile completing. And starting off with task 1, essentially, we get this tip that there is someone trying to possibly deal with some confidential records and controlled items. So we were given this file of possible forensic evidence, and we have to try and figure out what's going on. So starting off with the file itself. The file is named shipping.db, but as all forensic analysts learn eventually, the name of the file doesn't always tell you what's inside. So I ran file on it, and it said that it had zip data, which obviously is not going to be a SQL database or some kind of Excel sheet or whatever. So then I started looking a little bit more. I started looking at .db files, and eventually, after unzipping it, I was able to find some metadata about it that confirmed it was an Office document. So it's not your normal .doc or .docx, but we should be able to open it with LibreOffice, which I believe is called out in here exactly. Yeah. It was on a Linux x86 machine, and it used LibreOffice to actually view it and edit it. And then inside of this, essentially the document looks a little something like this. It's a white blank document with a bunch of rows in a table, like a lot of rows in a table that all kind of follow this general data scheme. So you'll see this first one is some kind of title. The next one is some kind of address. And then you have a name, a number, an email, another name, another number, another email. And then this one kind of looks like an ID once you expand it. And then you have, I believe that's a timestamp, but we can check the next one. Yeah, the next one's a timestamp. So once I kind of got it just for the data, I added these column titles for each of them. And I threw all the data into an Excel sheet, just copy paste the table. It was pretty easy. And with my one business class from high school, I learned something about a pivot table, which allows you to kind of group information. So if you want to easily be able to see everything at this address and an information based off of that, you can use pivot tables. And once I did that, there are these, and also here's how to do a pivot table inside of the LibreOffice Calc application. Just insert pivot table, all the data, and then in the row fields, not the column fields, you put all of the header names. Then once I did that, there are these large chunks of white space where that title, address, name 1, number 1, email 1, name 2, number 2, email 2 was all the same. But I noticed that there was this one outlier where the address was different, even though the rest of the information was the same. So that immediately told me that this is the ID I was looking for the transaction. And then essentially, yeah, this ID right here is just all I needed to submit, and that was task 1 done. Next up is task 2. So now that we have that possible APT threat, we have alerted the FBI, and the FBI does a raid on the location, and they find a bunch of empty boxes with programmable OTP tokens. So that's going to be your sticks that you can use instead of Google Authenticator, the USBs. And we also see that they are trying to get defense industrial base companies that produce critical military hardware. So a very bad thing right now. And then the FBI sends a cache of a bunch of equipment, and we end up with this one zip file of a bunch of other files. And supposedly these are backups, so we need to try and figure out what's on them and get hashes of all of the files that are on the backups. So looking at the downloaded zip file, these are all the files we get. They're all just this log sec and then some random ID looking thing. And there's one without an I, then the rest have I's. Once again, we run file on it, try and figure out what it is. And this is it's a ZFS snapshot. If no one knows what ZFS is, don't feel bad. It's an enterprise piece of software that's used for file management, file backup, and all that kind of stuff. So most of us haven't interacted with this before. I know I hadn't, so I had to learn all about how ZFS works. Well, to start, we need to be able to create a pool and an individual disk inside of that pool that's using the ZFS file system. So I found this great article about essentially how to set up virtual disks on ZFS, so I could kind of get started. It was super easy, pretty much. I ran this command, which got the an image that I had created set up in this pool, and then I listed it to make sure that this image and this pool were actually existing. And then I was able to create a test disk using that pool. And if you want to know how to create this image, I believe I have it in my notes. Test 2. Yeah, if you want to create an empty disk image on Linux, you can use DD, which essentially extracts the memory from a device or a file. And I just pulled from dev0, which is a device that automatically outputs zeros. And I put it into this disk image. I did 1 megabyte block size and 64 blocks, which is 64 megabytes. So that's how big the disk image was, based on essentially how big the files in the zip folder were. So then once I now had my pool and my disk, I started to import things. Well, looking at that -I, I learned that those were incremental backups. So you start off with this base file, and that's kind of an initial backup of everything, how it is. But it would be a lot to try and store that much information every single time. I mean, if you have 64 gigabytes of information, or like I probably have 100 or so gigabytes of information on this laptop. If I made 100 gigabyte backup, like even every week, that's a lot of data to store eventually. So what backup things do instead is they'll create that 100 gigabyte backup, and then they'll just track changes from then on. And then all they have to do is back up the changes. So once you get the initial backup, then all you have to do is just add the incremental ones in order, and it will kind of create the current state of the device for you. But we don't know what order these are in. And I tried increasing order for the numbers, and it didn't work. So all we have to do is brute force the order. So I wrote this quick little Python file that essentially goes through all of the files, and it will try and add all of the increment files, and then all but the one that succeeded, and then all but the other one that succeeded, and just keep on going through that. I think that had some problems, so I ended up just doing, try and do all of them, and then all of them, and then all of them for as many as there are, because eventually that will all of the increment files. So I printed that out, and then you could just copy the commands and do that. And as you can see, the command here is you just have to cat the snapshot file and then pipe it into ZFS receive F and then your test pool and test disk. So that's how you actually receive the information onto the disk. Just make sure you do it with this initial one first, and then you can go through and do it with all the increments. And then to find all of the file versions, I had to learn that ZFS has a very, very, very secret backup location. So I actually still have this test pool and test disk mounted. So if we do an LSAL, test pool, test disk, we see we have this IXFS and planning folder. So even if we do this and then do it recursively, we have all this information. But where are all the other files? This is only the current files that are on the machine. Well, even Linux tools don't always show you all the files that exist on there. So this TAC-A normally shows everything that's like a hidden folder, but technically, this .zfs folder is even more hidden than that. So this is where all the snapshots are.
Wait, how the hell ZFS is in the kernel, is my understanding, so they're in front of that. It's just the system call to look in that directory.
Yeah.
Wait, so there's a kernel modification that
It ships. It's a default. It's a very common kernel module to be included.
Mm-hmm.
I hate that. I really hate that.
That
So, yeah.
that backup system, by the way, is that how ButterFS does it too?
I know nothing about ButterFS.
Like, why even hide it?
You can't do this.
Yeah, assumably because you're not supposed to see all this. This is all backend stuff.
So there's just like a ZFS specific kernel module that's like, hey, you know what? When you search for that, you're not gonna see.
Oh yeah, you have to
It's probably the other way around. When you try to go to that directory, if it sees that you're on a ZFS drive, it's like it doesn't intentionally hide it so much as it's not a real file. It's completely virtual.
Yeah, if I had to guess, it's not indexed necessarily.
So it's not actually an index file. It's a
Yeah, because similar with how memory management works, Your program will have a list of all of the memory locations it has allocated,
Yeah.
but you could just allocate memory, not assign it to the program, and then as long as you know the address it's at, you can still reference it, and you can still do things with it. So if this isn't essentially
So it's like
connected to
it
the folder,
has- yeah, it's like in terms of operating system, when we studied that collaborating system, it has, goddamn, I don't remember the prefix,
You
but
could-
it has data blocks, but it doesn't have the inode block corresponding.
Not even that. Like,
or like maybe the inodes aren't connected, because each folder is supposed to have.
you can think of like the /dev file system or the proc
Yeah.
file system, where those aren't.
Those aren't actual files, those are.
Yeah, they're interactions with either physical devices or the kernel.
Yeah.
Yeah.
They're interacting with software somewhere.
Oh, so this is actually a software.
Yeah.
So this isn't actually really on the file systems.
Yeah.
Mhm.
I hate that so
So
much.
then in this scenario, it wanted us to have a SHA-256 hash of all of the files. And the easy way to get a hash of a file is this hash name sum function. There's MD5 sum, there's SHA-256 sum, there's probably a couple others. This is great if you're doing any forensics work or any malware work. Being able to search an executable file by its hash is very useful, because of course hashes known for not colliding, or at least if you have similar data, it gives you quite different hashes. So that way you can easily tell if it's been modified or if it's a recognizable file or what have you. So an easy way for me to do this is I found out that this pages folder was the only one that ever actually changed in the backups. Because you have, the logsec folder and the pages folder in the normal thing, but this logsec folder is the same from the very first snapshot to the very end one. So I was able to just do this. Inside of Linux, star, or I guess inside of bash, star will automatically essentially fill in all of the folders that's in that folder. So this will fill in all the snapshots, this will fill in all the things in the pages folder, and it'll kind of do that, what do I want to call it, like recursively. So it'll be, snapshot 1, file 1234556, snapshot 2, file 1234556, and it'll do that for all of them. And then we're going to pipe it into awk, which is a great Linux command line tool, where we can print out the first column of the output. That's what this does. And then we're going to append it to out.txt. And we're going to do that for the logsec folder and the regular pages folder for what we end up with. And then because I'm a Vim nerd, I decided that the best way to do this would be vim out.txt, and then you can use this great little command, and it will automatically sort and remove any duplicate lines in your file. So that gives me a sorted list of unique hashes for all of the folders.
That's
And then-
not using a Emacs Vim hybrid.
Oh,
The
no.
window manager goes into it.
I'm pure Vim. So then once we had that, we could just submit it. I guess if you guys want to see how many file hashes there were, I should still have. That's what it's in. There we go. Yeah, that's how many unique files there were. And you can see it is sorted. So you start with 0 on top, and you go all the way down to F on the bottom. Now we're into task 3. So this is where the rubber hits the road. There were like 4,300 people signed up for this. 2,600 or so got task 1. Around about 1,000 got task 2, but then only, I want to say only around like 150 got task 3. Task 3 was a major jump in difficulty that a lot of people struggled with. So let's jump into it. Now that we have found all the files, let's see. They found out that Guardian Armaments were the people who are having all these problems with the software and hardware tokens. We're going to be dealing with some malware reverse engineering now, my favorite. What it's doing. Oh yeah, so then they were able to find a USB drive of the program to essentially create a bunch of hardware tokens. So we are given this program and another file. The server program, as we can see with the file command, I use it on every file I get. It's just useful. It is an ELF, so executable link format, your classic Linux executable. And it is also a Go program. I remembered reverse engineering Go from last year.
No terminated strings, don't they?
Correct. Go doesn't. Essentially, every program stores all its static strings. So if you're going to print hello world, it's going to store hello world somewhere in the program. And normally, that is terminated with hex 0 or a null byte that indicates the end of a string. Well, Go decided that strings should actually be immutable objects, so you can't change the data in them, and that object will hold the address that the string is at and the length. So you don't need null bytes in Go. So all it is it's a series of characters with no distinction of where one stops and the next one starts, which makes it really hard to reverse engineer until you start actually getting some of the code flow down, and you notice that, well, this memory address is accessed here, and this one is accessed somewhere else. So everything in between here is probably a full string. So then you can start to extract that out into different chunks based on what is being referenced in other parts of the code, which is how most of the Go string parsers do it. And then you can also see it has debug info, and it's not stripped. So all the function names that it uses, we are going to get them, which makes it so much easier, as you guys will see in part 2 with a stripped Go binary. And then we also have this file, Jasper_0. I was very confused what this could mean at first, and then I remembered all the way back to task 1. As I said, these build on each other. We have this guy, Jasper_0 5038 at guard.ar. So I'm assuming we're going to have to do something with his email. So moving on from that, I decided for this we're just going to have 3 different sections. We're going to look at Ghidra. We're going to talk about gRPC and protocol buffers eventually. We're going to look at how to interact with the program and then how to solve it. So starting with Ghidra, we're just going to open up this program. I have a couple of comments in the code which will make it a little bit easier to understand. But I'm going to be showing off generally how it works and then the vulnerable part of the code. So I know this is a lot, and we're going to have to look at assembly. Go does not, what am I thinking? Not disassemble. Decompile well. Doesn't decompile into C very well because it has a runtime. So it can make calls to that runtime, and if you notice instructions like this, no instruction, dword pointer, RAX plus RAX times 1. That's not a real instruction. So I haven't looked into it, but likely this is a call to the runtime manager to do something. So as you can see, it kind of jumps between things and it has different threads, and the code flow is not always obvious. But if we look at the functions, we have a lot of functions because it's statically linked, so everything that's ever imported is also in here. So if you kind of like, I don't know, jump into C.
I think how it's statically linked to the goddamn the amount of time you have to spend if it's not like actually linking the libraries manually is hell.
Usually with dynamically linked, it'll link to the library name. So then I just look up the reference data for the library name. So like,
one time I didn't recognize anything.
It's like I can look up this go and then context.cause and figure out how this works. Because this will likely have some kind of data, and we can figure out what this function does from here. Context dot cause is somewhere. Here we go. No, whatever. So then you can look at the documentation and figure out what it's doing. But if you really wanted to, you can look at the code and see what the code's doing instead. So with all this, I figured best place to look whenever you have a statically linked file is usually something called main. So I pull open M, M-A, M-A-I-N, because all the math libraries are also in here. And then we can see a bunch of these functions. In Go, it isn't the main function, it's the main.main function, apparently. So this is actually where all the code will start. And as you can see from this first bit's actually kind of understandable, but afterwards it starts to just fall apart. And even people who understand C code would struggle to try and understand what this program is doing. And even people who understand assembly code would struggle to try and understand what this program is doing eventually. So instead, I just look for function calls. So I notice, printf, probably going to be printing something. And then we got some OS args, and then some flags looking at arguments. And then we have this auth server IP, so probably another argument in there, and the log level as well. And if we hover over these, because Ghidra is really nice, we see OFNI, and then all we have to do is remember little endianness, so the bytes are in reverse order. So this is actually just the string info. And then we also have, I believe this is, can you? Or, I don't know. Well, it's not always little endian. I think a lot of the Go hex stuff was little endian, like the embedded hex things. Yeah. And then this one, you had Giba.
Oh yeah, okay, I figured out how to use it. Can you change the Ghidra preference to change the endings?
I don't know about preferences so much as that there probably can be like a little, there's only a way you can do it, but it might be like you have to write a little bit of code that handles it.
Yeah. Because even with the LSB or least significant bit executables, sometimes it'll just be an array of characters, which is how most strings are stored, to be honest, not hex values. That's probably why Ghidra is throwing a fit here. Most of the time when you compare strings, you're going to look at a byte and then look at another byte and then look at another byte. There's actually assembly instructions for that. Instead, Ghidra just looks at chunks or Go just looks at chunks of 4 bytes of data, which is why it looks so weird. So yeah.
So it's like a fixed word size it operates on?
Mm-hmm. And Go also does a lot of vector instructions for comparing strings. Which a vector instruction, CPUs have essentially 2 different CPUs inside of them. They have an integer one, and then they have a vector one. The vector one just works with arrays of data at once instead of one like character or byte at a time.
AVX is pretty awesome. I'm not gonna lie.
Yeah, you can. Intel has full documentation on all the vector instructions if you really want to get into that. I have just because I think it's fun, but it's very in the weeds.
If you know how to use it, I made like I think it was a find the maximum value in like a massive array program. Runs 3 times faster than handwritten C.
Oh yeah, writing an assembly can be quite fast.
Yeah, you can get stupid fast.
Looking at this log level, so we've seen the info. This is debug, and then we also have error. So we got 3 different log levels there, which is kind of useful. This will tell the user the log level is invalid. So if we kind of start to get into the Go strings here, we can see that this is a Go string. It's a bunch of characters and it's not null byte terminated. But as I said before, if we look at what is referencing what addresses, we can kind of tell where the strings start and end. So we have this invalid log level colon %s and then 0a, which is just a new line. Anyone who's ever done printf before will know this is just filling in a string, and we'll print this out. And then the next byte, we have what looked to be a completely different string. And if we don't want to worry about that anymore, Ghidra has this really nice thing where we can select this chunk of data, go to data, and then if we just turn this into a string,
oh no way, that's awesome.
it will automatically turn it into a string in the code.
I didn't even know you could do that. That's fucking
Yeah, so that way it's a lot easier to read. And I've done that a couple times.
Off with Ghidra, I'm not gonna lie.
Oh yeah. Ghidra's really nice, and it's free. IDA is expensive, and Binja is not terrible. But Ghidra is free, which is why I love it and why I use it. And also why the NSA does so many reverse engineering challenges during this competition.
free advertising.
So I'm kind of like looking through here. I don't know. We got like new objects, log levels, this like right barrier thing. If you want to look into Go stuff, this is interesting.
Like right barrier for like parallel stuff.
Yeah, for like new objects and all that. It's weird.
Like parallel program, parallel operation kind of.
Yeah, it goes like natural and multi-threaded. So it automatically does multi-threaded stuff even if you don't tell it to try and optimize itself, which is why it runs so fast. Error string. Oh, here we go. This is something fun.
Ooh.
Main.main with transport credentials, func1. Okay, so we're doing some kind of transporting thing. And we're also we're messing with google.golang.org/grpc/credentials/insecure.insecure.tc. So this tells us that we might be dealing with this package, or this package will be important, this gRPC package. And I'll talk about how gRPC works a little bit later because I had to learn a lot. And this is a little bit more obvious. We create a new client and we look to be dealing with some kind of IP. Is this a string? No. That's just a variable that we use. Okay, all these are cool. So we have a new client, and we also create a new server, and we have these functions, which are a little bit more interesting. New cgen auth client, and register seed generation service server. So these are going to be our two kind of main functions. We start off with this auth client, which is going to be doing some kind of authentication. And if we look in here, we can see it does a gRPC call using the auth service client class, and it does a ping call. Checks the result, and if it works, it will return. Don't trust any of the function parameters or return statements. Go doesn't use what Ghidra thinks it does. I'm pretty sure for function arguments it uses like RAX, RBX, RCX, RDX instead of the traditional Linux call stuff. And it also just returns whatever, wherever.
Wait, does Linux not store its first few arguments in the registers?
It does. Well, okay, depending on the calling convention, but you guys can look into that later if you want.
Oh god, I'm having flashbacks about ABIs.
Yeah, you'll learn about this in 538 if you want to take reverse engineering with Burke. Highly recommended. He's going to talk about the different assembly calling conventions. But normally it is RCX, RDI. What is the fast call convention? Because normally Ghidra handles this for me.
So we got stack ranks and stack
I think Microsoft actually is a good thing on this. People will clown on Microsoft. I love their documentation though. If we go down to where is your pass in registers and possible. There we go. First arguments are passed in ECX and EDX, and then I'm pretty sure Linux also does RDI and something else. Come on, where is it?
Oh god, I just saw the word Objective-C and I died a little bit inside.
I will find this later and I'll post it on the Discord, what exactly the calling convention is. Because in cDecl is also pretty popular, where you put the arguments on the stack in reverse order. You'll see that a couple times, not too often. Wait, let me check the chat. Okay. So, with that, as I said, we're going to be doing a lot of reverse engineering. This one took me a lot longer than 2. I will assure you guys that. We know we're going to be doing a gRPC call to the auth service client. We're going to be pinging it, and then likely checking the response and going with that. If it's successful, we're going to be opening up our C generation service server, which doesn't seem to do much. As I said, looking at the C code doesn't tell you a ton. We're calling this random code variable and whatever. Like, it's really hard to tell exactly what this is doing. So I prefer dynamic analysis.
Oh god, you're gonna run it.
Yeah, dynamic analysis, especially in a competition like this, is usually okay. If you're dealing with real malware, VM.
I'm pretty sure, from what I remember, anytime there's been something even potentially like sort of dangerous and it might damage your machine, type binaries for Codebreakers, they have very clearly, like, in big bold letters, bright red, had "do not run this, it is dangerous." So, like,
Yeah.
at least in this case, like, it's
Yes,
for NSA
we'll run
Codebreakers,
the
usually
NSA
safe.
program on the machine.
Or I even Hack the Box. They have their Sherlocks now, and you can do malware analysis in that. They have a disclaimer that is like, this can do bad things to your machine. Make sure you're following these safe practices. Here's the password to unlock the zip folder. Make sure you're following that, because it can actually just encrypt your hard drive, like one of the challenges I looked at. It didn't for mine, luckily. So if we go into task 3 and we pop open the server, we get this. We can see it tried to ping the auth service and it got no response, with an RPC error saying unavailable destination, and it's trying to dial 127.0.0.1, port 50,052.
What runs on it?
gRPC. Most of the gRPC examples you'll see, which I'll cover a little bit later, use 50,051 and 50,052.
I really should have known that.
It's just what they like to
And
use.
Audi.
Yeah. So to learn a little bit more about gRPC, I did a couple of slides on it. So it stands for Google Remote Procedure Call. RPC is a general thing. Google created their own thing, and it's implemented in Go, Python, C, .NET, a couple of different things. But yeah, we're going to be looking at the Go implementation. It's completely open source, I believe, and like free to use and everything, so it's super cool. And then it's a wrapper, essentially, around the HTTP slash 2.0 protocol. So a really easy way to tell this is to just set up a netcat listener. So if you do netcat LNVP and then 50,052. So essentially we're going to be the auth client for a little bit. It's going to try and connect. And we get this typical like HTTP header, PRI star HTTP 2.0, and then random data after that, which this is the start of HTTP 2.0 handshake that we don't know how to respond to properly. And it's going to time out here. So it's very similar to WebSockets a lot of the time, because a lot of the times people will use it for data streams, either unary, which is one source streaming data to another, or what is the other one? It's not binary. Or essentially both ways streaming, where both services will be streaming data to each other and keeping that connection open while it's streaming data back and forth.
Wait, so it's either going both ways at once, or one way and then the other way? Or
You can kind of think about it like if you're like streaming on Twitch, you could just have a raw video feed that's just shot to you over and over and over and over and over, and just like get that consistent stream of data without you really interacting with it, other than saying, hey, can I have this data stream come to me? Or you could have, you know, two people trying to stream at the same time, stream data back and forth. It can do both, and it also doesn't have to be data streaming. This challenge doesn't use data streaming at all.
would that be full?
Yeah, it'd be full. Here, we can pull up the gRPC documentation as well, because it has diagrams.
Oh my god, it's got diagrams.
Let's go to learn more. I think this is a good place. Yeah, that's really good documentation. So, and it also uses protobufs for all of its calls, which we'll talk about a little bit later. So you send request and response, pretty classic. This is protobuf stuff. Okay, let me go to protocol buffers, where we can have, where is the stream? Yeah, data streams. Where is the streaming stuff?
So you set access for the internet.
Where's the service specification? Is there? Okay, I'll find out where all the documentation I used was, and I can link that later. But yeah, so it can do data streams like WebSockets. This one doesn't use them, but more specifically, it uses protocol buffers. You have to use protocol buffers to interact with it, and you have to know what the protocol buffers that the server has are. So then what is a protocol buffer? It essentially defines a service. So any kind of like API endpoint, it'll define what the endpoint name is, and then what the request looks like, and what the reply looks like. So here you can see a basic greeter service. It has a say hello endpoint that will take the hello request object and return the hello reply object. And that is the basics of a protocol buffer. So with that, I knew I needed to try and interact with it in some way. So then I figured out how to try and, let's see, do I actually have it in here? Figure out how to extract the protocol. Oh, actually, it's just a program in here. Figured out how to try and extract the protocol buffers from the Go program itself. I used, what is it called? Oh, that's right. Go. I think it's called protodump.
Is it built in?
I had to install it.
Oh.
Ghidra also had, I think Ghidra did a little bit with, like, I think Ghidra, I did it all through Ghidra when I did this challenge, and Ghidra rebuilt some of the proto buffs, and they've got names that were recognizable, and I just kind of like correlated the types to the names and things.
You can actually find this in here. So, well, we know that we're looking for this cgen auth client, so if we want to figure out more about what that's doing, we can look up cgen auth. So we see we have the main stuff, and then we also have some types here. Is it going to be in the types? Here, let me just do auth. Main.
It was a lot more difficult because I had to go like rebuild it. So like it was like,
There we go.
it told me it was a type, but I didn't know exactly what type that was from the real protobuf types. And
Yeah.
things like that, so it was a little bit more work.
So you can see it's pulling an auth gRPC, and it's pulling in some of the proto stuff here. And then even more gRPC, and then we have each of the service descriptors. So message types, and where are the service descriptors? Well, we know ping's one of them. There we go. So we have the auth service client, and we have this ping, and then we also can see the descriptor, and then when it compiles, it automatically generates functions in Go that can then be used by the Go program. So we have like get ping, the proto message, reflect, reset, string, all that kind of stuff. And that actually will show up in the protocol buffer itself.
And protocol buffer is a Does it go object? No, I need that.
It's a file protocol that then gets compiled into a Go file. So it's like full function definitions, variable types, all that kind of stuff.
So it's its own thing that can be compiled into.
It can be compiled into Go, Python,
Okay, yeah.
anything like that.
So that has the convenience of having you can have the same protocol buffer definition for multiple languages.
Yep. So you can have your Go.
Really nice.
Yeah, because I initially did this in Python. I extracted the protocol buffers and then I wrote my servers and clients in Python. But that was being a little bit slow, so I decided to rewrite it in Go. What was it called?
How hard is Go compared to something with Rust?
Go and Rust are very similar.
Okay.
So if you know, it's Go bin, okay. So yeah, I installed this proto dump program. So if we just do proto dump on server, file server, we can see it automatically creates these proto files, which I technically already have them in a protobufs. Yeah. I already have them all in here, and we can see our auth.proto, which is our auth client, and cgeneration proto, which is the cgeneration server. So if we take a look at auth.proto, actually let's do cgeneration proto because it's smaller. We can see the service, we can see each of the RPC calls that we can make to it, along with what the requests and responses are supposed to look like. And then now that we have this protocol buffer, we need to compile it, which if you really want to learn how to do that.
So are those signatures or are they actually?
It's best described as like a description.
Yeah.
So let's see. Because there's no code in there, it's just like variables.
Yeah, it's a description of the protocol.
Okay.
Maybe a good example.
Because I can show some compiled proto buffs, I believe. Right? Yeah, so we can see this auth.proto got turned into auth grpc pb.go, auth pb.go, and I think that's it. So then if we take a look at these, it is just a Go program that has, it imports a couple of like gRPC packages and stuff that it needs. And then it sets constants for these are the endpoints that you can hit to try and essentially make calls to it. The interfaces, and then like this authenticate call. It's going to take context, it's going to take all the auth request data and then gRPC call options, and it's going to return the auth response and or errors. And then you can see it does all this, and this doesn't implement it at all. This just kind of makes it available. We still need to actually implement it.
Okay, that's what I thought.
Yeah.
It's somewhere between a signature and a wrapper. Actually, that's not a good description.
I would think of it like a library description. So like when you go look up like what does this function do in C, and you'll get like the man pages for it. And it's got like function name, what it can take in, and then what it does. But you don't actually care about the code inside the function. Just that that's how it does what it says it does with this data that goes in.
Yeah, I understand it. It's, I can't. I don't know what to describe it to someone else.
And then gRPC also has a great getting started thing for C#, C++, Dart, Go, Java, Kotlin, Node, Objective-C, PHP, Python, and Ruby. So a bunch of different languages. So you can use gRPC with whatever you actually want to make the service with. This will tell you how to do everything, get it going, and then they have this examples folder inside of the gRPC repo, so you can look at all the different examples of how things actually work. So then once you do get your proto file, you have to do this proto C, then that'll actually compile it into whatever language you're going to be using. And then you have to update your program to implement these functions, taking the context and everything, and actually do stuff with it using the protobuf. And then once you do that, you can just run it. But,
So it is. Okay, I'm not gonna try to explain.
okay. I made.
It's incredibly familiar in what it is, though.
Yeah, it's similar to an interface, but not quite. I don't know.
Yeah,
It's
but
all.
I know I know conceptually what it is and what it's
Mhm.
doing. It's just that it's slightly off any schema I have for.
Yeah. So then inside of this, how you actually import protobufs is a little bit different than normal things in Go. You have to specify it is a protobuf. And then, as you can see, I immediately just kind of parse the flags with the port and everything, type server, and then I set up this authentication function that'll take in the context, auth requests, and all of that. And it'll automatically return auth response true, because I'm creating the auth server. Why not just let all the authentications work? Same with registering the OTP seed and pinging it. And I just set this response to a random value so I could identify it in network traffic if need be. And then after that, parse the flags, listen on the port, set up the new server, and register it. Let us know it's listening, and just keep going. So then that'll be listening. Now, if we, and I guess we're technically over time, so if anyone needs to go, they can. I'm probably going to finish up task 3, and then we can do 4, 5, 6, and 7 next time, or see as far as we can go.
And will you put the slides in this?
Yeah, I'll put the slides in the Discord. This is also a live stream, so I'm going to keep going if you guys want to watch the rest of it later.
I'll get the key.
So inside here, all we have to do is do go run server.go. Now we're listening on that port. And then if we hop out, we can look at the options here, where we can actually set the log level, which will be useful, because whenever you're doing active debugging for reverse engineering, I always set the log level to debug. That'll just usually get us a little bit of extra information, if need be. So yeah, we can see now we have the auth service up and running, and it gave the pong that we want, and our cgen server is running. So this is now the server. So now we need to make a client program to be able to interact with it. With that, I just created a simple client server. So you'll see it's a little bit different. We don't need to implement a bunch of the functions, but we do need to reference them. So once again, parse the flags, create a new client, and then register the new client, timeout, and then we can call a bunch of the functions of the client. So this is calling stress test for a large amount of time, which we'll be talking about what the vulnerability is later and why I would be doing this. And then I also did a bunch of multiprocessing things. That gets a little bit more complicated, but you don't need to do that and you don't need to worry about it. So then this is how you would be able to actually interact with the server. Didn't I do a different client? Yeah, that's right. I have a simpler one. Yeah, there we go. So this is the normal client that you would really need. And the basic function that we actually want to see, this get seed, where we just pass in a username and a password. It'll authenticate it, and then it'll try and get us a seed. So we can see how that works now. Now that we actually have the server up and going. So if you do go run point copy, we see that we have a seed and account. And if we just kind of check over at our server, you can see it got a get seed request. It is authenticating. And it said, oh, look at that. Test user authenticated but has no privileges in network, so no need to authenticate with the auth service. So that was pretty interesting. I wonder why we're not trying to authenticate with the auth service. And then if we try it again, we'll see we get a new seed, a new count, incrementing by 1 each time. But we're just authenticating with the auth service this time. So now it actually reached out to the server. It hit my auth server that's running here. I don't have any logging on it currently for efficiency when I was trying to brute force this. So it hit this. That responded with true, and then this was able to just keep on going. So it registered it with the auth service, and then we got the username, seed, and count. So with that, I was like, there's got to be something weird with this get seed request. So I decided to look more into it. Oh, that's not going to help. Go away. So once we get back to main, we will see that there are a couple actually implemented services. So we have this auth service, get seed request, and then the stress test request. This ping is technically here, but it doesn't really work, and this test embedded by value. Both Trent and I were thinking it might be doing something. It didn't seem like it was doing much. It technically gets called a couple of times. I don't know exactly what it's there for, though. And it's not important for the solution, so. Looking at this get seed requests, once again, we're not going to care that much about the actual C, but we can kind of see we get a username, gets converted to a string, password converted to a string, going to log something, and then, oh, look at that. It's calling the auth function here. Well, what does the auth function do? Looking at the auth function, we're going to generate a random integer and do something with a password. And then it compares it with this random byte value. Well, because I know the C code isn't that reliable, I started to look at some of the actual assembly code. It's kind of hard to understand this until we look at how it gets registered / created. So let's jump over to new cgen auth client. Interesting. It calls math rand seed, and as we see before, Ghidra is not that reliable with actually putting the right function stuff in there, and it's pretty easy to assume that if this gets thrown into RAX right beforehand, that's probably the argument that's going into seed, because seed only takes one argument, as if you look up the documentation for it. So you can see that all of the random numbers are seeded, and it does that at the very start of the program. And then somewhere along the line, it generates a random number. Both are very important, and it took hours for me to actually figure this out, of essentially sending requests, sitting in GDB, kind of like looking through it, looking through the calls, looking through everything worked. So I'm just going to breeze over it a little bit, even though it takes a little bit more work when you're actually trying to solve things like this to figure out what everything's doing. So we generate a seemingly throwaway random number, and we know that all of the randoms are seeded. And if we actually want to go test this, well, we can just kill this, start it back up, and let's see what seed we get. Same one as before. So we know it's reliably seeded. What's up here? Oh, that's a little bit small. Here we go. So now that we know it's reliably seeded, we know that there is some kind of reliable way to get a seed and a count depending on certain data. Looking more into the auth thing and looking more into this specifically. I noticed we're comparing with EDX. Well, what's an EDX? So I go back here, REX to RCX. It's getting jumped to from here. Oh, R15D to EDX. And then that is called from like either here or here or here, like a couple of the ones down here. So then what gets put into this R15D? Well, it's R12 plus RAX times 1. Well, what's an R12 and RAX? If we kind of follow up here, eventually we kind of see this is the start of the main loop that we're looking at. So I pulled this into GDB, and it's pretty easy to tell. Username data gets put into R12. Username length is in RCX. And then this was that thrown away seed that was initially generated during that first request. So when I'm doing that first test request, the thrown away number goes into this RDX. And then EAX is cleared. Jump down here. If RAX, so that is essentially this 0 number. If RCX is less than 0, which it won't be the first run around, we're going to go to this authenticating log, which is what I named the function to make it easier to look at. And why did I call it that? Well, there's a string in here called authenticating with the auth service. And then there's also this test user log, which is where I found the test user authenticated but has no access to anything. So naming functions can also help when analyzing things, so you remember what is where and which functions are doing what. So now that we know that we'll be essentially trying to authenticate once RCX is less than RAX, we can watch how this works. This is a really interesting way to add forward RAX and then compare it to RCX, because this takes the address of RAX, which is 0, adds 4, and then puts the result in R13, compares that to RCX. This essentially will check different lengths. So the gist of what this is doing is it'll check 4-byte chunks of RCX, and if it is, if there are 4 bytes left to check, it will throw those 4 bytes into this R15D, which is a 32-bit register, and it'll take the R15D, XOR it with EDX, which, if you remember from before, was the username string, or was the seed. So it takes the 4 bytes of the username, XORs it with the seed, puts it in that seed value, and then it will move R13 into RAX, which is essentially our increment counter. On my website, I actually have some like generic Python code, which generally shows how this works. If we go to Codebreakers test 3, I have some Python code, which is a little bit easier to read for this. So you can see for I is less than username.len, temp is equal to whatever. If that's that, we'll check the different username lengths, and then we'll essentially just XOR the result with temp. And then after doing that enough times, so after taking the 4-byte segments of the username and then XORing it with the seed, it will check the resulting value. So that is how we get to this test user authenticated but has no privileges. And we know that with the seed that we get initially and the username test, that 4-byte value, if we XOR the two, we should get this result. So I wrote a quick little Go program. I think I removed, yeah. I wrote one that just essentially, do I still have that? Yeah, that just seeded the random and gave me the 3 first numbers, which I was able to tell this does work with the test thing, and then this is that first seed that we get every single time, and then this third number is that second seed that we get every single time. So using that, I seeded the random, generated this, got the old seed, and every time we can try again and try with a new seed, and we just need to know what username will get a specific seed and count. So then based on the clippings that we saw earlier, I knew that the username we wanted was this Jasper underscore 05038. We wanted to see what seed and what count we would need for it not to authenticate with the service. So it's essentially skipping authentication, but still getting the hardware token. So I wrote this quick little Go script because Go uses its own random seed stuff. So it was easiest just to kind of keep within the Go realm. You take JASP in little endian. So this is JASP, all lowercase. And you XOR it with the old seed. And then you take ER underscore 0, XOR it with the result of that, and then this is the 5038, XOR it with the result of that. After you do that, increment the count, generate the seed, which is going to be the next random number that you're going to get, and then if the result is equal to this, we can then print the success message. So if I just do go run solve.go, we can see it does quite a few requests before it actually tries to find the seed. So initially, I had a client that did this by talking with the server and sending the username every single time. Let's see, if we check the number this is, so 000, 000. So this is going up by millions, I think, each time. So we end up with 3,456,000,000 requests I would have had to make. I was getting about like 10 to 100,000 a minute. So as you can tell, that would have taken me weeks to try and brute force that way. So I'm really glad I ended up making this script. But eventually, we get this username, seed, and count. And if we look back to the scenario, it wants us to... Oh, I guess I don't have the actual thing. Yeah, enter a valid JSON containing the 3 interesting keys and specific values that would have been logged if you had successfully leveraged the running software. And that is that. So that's task 3. I have also solved 4, 5, and 6. 4 is going to be a lot faster. 5 is going to take a little bit. 6 is going to be a little bit as well.
If there was things you didn't understand from task 3, understand that's fine. I think I actively spent 100 plus hours on it, and I did not solve it. So like,
I usually put that much into it too. Oh, it's, as you can see, the extent of the extent of all of the testing I did. Okay, granted, that's a lot of Go files and stuff, but and PyCache. It's a lot. So yeah, all the protobufs, this random like listen py stuff. You can even see my initial Python attempts trying to figure out this stuff with the protobufs and trying to learn gRPC and protobufs as a whole in Python before jumping over to Go. I didn't know what gRPC was. I didn't know it existed. I didn't know what protobufs were. I didn't know what ZFS was. So that really goes to show that you can learn. You can Google your way into solving these challenges. Some of those base skills are still going to help. If you can't read assembly in the slightest, or you're really struggling with Ghidra, task 3 is going to be a lot harder. Knowing Ghidra, knowing how to reverse engineer helped me a lot. But you're still going to be learning things every single time. You're not going to know the services that whoever is using in all of your different engagements. So you're going to have to learn. You're going to have to learn the exploits. You're going to have to do research. And that's what this is really good at teaching you. So I guess that's it for my presentation. Any questions, I guess?
Would you recommend people do this?
I would heavily recommend people do this. Talk about a resume booster. As I showed, all of these are up on my site. If you guys want a more thorough walkthrough, or want some help with something I talked about or glazed over that you want to check. Oh, that didn't update, that's fine. I have all this stuff on my website. And also, if you want to read ahead compared to the rest of the class, I have all the way, I think I have task 4, I don't have task 5 in yet. It's a little sneak peek. Yeah, I don't think I have 5, yeah.
I have one question.
Yes.
For this kind of stuff, how do you know you're heading in the right direction instead of being caught in something that's
As I said, I got caught in things that, like trying to brute force it with the calls. That was a bad idea. I had multiple nights where I just had my laptop going. I left it going for like 12 hours and it wasn't hitting it. And I'm like, it's probably not this if it's taking 12 hours. I was looking into the test embedded by value for several hours. I was, what else? ZFS. I really struggled with that one. That one took me like 10 hours, 15 maybe, trying to figure out how ZFS works. So when to figure out when to give up or when to try a new direction. I would say when it feels like you're kind of scraping the barrel for ideas, you'll get an intuition for it eventually. You can go to a broader sense, take a list of all the components, and then if you really want to, you can just kind of do a brainstorm of like this component might have these vulnerabilities. So then you know what vulnerabilities you might just want to take a quick look into just in case. Like for this, if you just wanted to like look into gRPC vulnerabilities or check the Go version just in case. Maybe there's like a CVSS 10 critical vulnerability of that Go version that it's trying to use. Just kind of take a step back, try a couple different things. And if nothing else, especially when it comes to reverse engineering, start documenting all the functions. What does this do? What does this call? How does this interact with each other? And get a broad spectrum view of everything. And that'll get you a better way to move forward.
Yeah. That's a hard one to answer because like you don't really know, but like it is just like it comes to intuition. Like if you've looked at this for a ton of hours, it just like when things are released, like in this case, especially like NSA Codebreakers, they might have a few red herrings, but they're not like intentionally trying to mislead you type thing. Like you'll find little things that click together. For example, like the multiple gRPC thing was like a really basic one that's the ping. That was one thing that I looked at. I was like, okay, I'm probably going to try at least some gRPC communication if they're providing this most basic thing that I can work with to build up to the next steps. It's like little stepping stones too.
And do more CTFs. I spent 4 weeks on task 5. I had thought of the solution within the first week. I just didn't know how to implement it. I didn't know the right words for it. So I ended up moving on to other ideas that were totally incorrect. But then as I kind of rolled back around to that solution, I was able to implement it and get it right. If I knew cryptography, I knew I would have been able to trust my gut there. And I would have kind of known the right vulnerability to go. So the more you do a specific category, the more you can kind of go, I think this is what they're trying to tell me. So doing more and more CTFs just helps. Yeah, you're welcome.
Oh, another one that there's a Discord server for NSA Codebreakers with a bunch of people.
Oh, yeah. Do OSINT.
You're not allowed to share answers off that, obviously. It's a big challenge. People still talk about it though. Like if there's a whole bunch of complaints about something on a task, you can be pretty well assured that you're at least somewhat on the right track if you're encountering that same problem.
Like last year, it kind of got out of the bag that task 4 required some brute force.
I mean, even then, like task 3, it was like there was a whole lot of reverse engineering talk about it. Even it just talks about like having to dig so much into Go code in a lot of places. They just talk about that because that's not like giving something away so much, but like it kind of is. Like if you spend a ton of hours reverse engineering this Go code, you can reasonably assume you're on the right track then because other people also are doing the same thing and talking about it.
Yeah.
like collaborative?
Not so much collaborative, so much as like
Yes, it is.
OSINT, like other people are doing it this way. What are the odds